So, as a reward and congratulations for having made it so far, we have a fun game for you to play. I was very excited when I discovered this game by myself and figured it out. I'm sure other people have discovered it independently over the years. But the way the game works is you pick a positive integer n, and you think of all the ways you can partition it. Partition is the fancy math way for saying write it as the sum of other positive integers. So partition a positive integer n into the sum of smaller positive integers. Now the question of the number of ways that you can partition an integer is an incredibly complicated question that was only finally proved around 100 years ago by the absolutely astoundingly brilliant Indian mathematician Ramanujan, working with a mathematician named Hardy, who we'll see later in Trinity at Cambridge, in England, the other Cambridge. For now, we're going to just concentrate on, of these partitions, which one gives us the largest possible product. So let's start with an example. Here are 4 ways that I can write 8 as the sum of smaller positive integers. Let's figure out what the products are. So here, 1 times 7, 7. 2 times 6, 12. 3 times 5, 15. 4 times 4, 16. Now you should be asking yourself at home, can you beat 16? That's the goal of the game, to get the biggest possible product. And remember, you're not restricted to writing it as just the sum of 2 integers. So for example, I could write 2 plus 2 plus 2 plus 2. That would also get me 16. Is there a way to beat 16? I could try 1 plus 3 plus 4. That only gives me 12. Is it a good idea to put a 1 in there if you're trying to get the biggest product? Probably not. Has anyone thought of a way better than 16, bigger product than 16? Well, I think I heard somebody say 3, 3, 2. Those add up to 8. And when I multiply them together, we get 18. So that is better than 16. So far, the winner for 8 is 3, 3, 2. Can you think of anything better than 3, 3, 2? You can pause the recording now and try to see if you can come up with one. In fact, you cannot come up with one. 3, 3, 2 is the best way to do 8. We're going to try to look for a pattern here. So what do you think is the best way to do 9? Could try 4 and 5. That gives us 20. 2, 2, 2, 3. That gives us 24. Probably somebody out there has guessed a better way of doing this by now. And you have come across 3, 3, 3, which gives 27. That's right. 3, 3, 3 is the best way to partition 9 to get the biggest product. We're going to keep going here, trying numbers until we see the pattern. So if you want to try to figure out the pattern on your own, please go ahead, pause it. How about 10? So here we had 3, 3, 2, 3, 3, 3. I suppose a logical thing would be to think 3, 3, 4. That gives me 36. Of course, any time that I write a 4, I could write 2 and 2, right? So I could also write 3, 3, 2, 2. That's the same. We're going to not bother to write that differently. Can you exceed 36? And the answer is no, you cannot. So let's go to 11. If we're following the pattern, 3, 3, 2, 3, 3, 3, 3, 3, 4. Seems like 3, 3, 5 is the next one. That gives me a product of 45. Can anyone beat 45? I can beat 45. Can anyone at home beat 45? I like having 3s. That seems like a good idea. How about 3, 3, but instead of 5, what could I write? How could I break up 5 to get a better product? Well, 4 and 1 is no good. How about 3 and 2? Now I've got a product of 54. Aha! So the pattern changed a little bit. 3, 3, 2, 3, 3, 3, 3, 3, 4, 3, 3, 3, 2. So if you thought you had an idea for the pattern of 2, 3, 4, 5, that wasn't quite right. Can you see a new pattern? So what should it be for 12? It should be all 3s. And then I think I get a product of 81. So do you see the pattern now? We put in a 2, then we do all 3s, then we put in a 4, then we put in a 2, then we do all 3s. So if you had kept going, for example, what would 60 have been? The numbers that were divisible by 3, 9 and 12, we used all 3s. So 60, I think, is using all 3s. And then we get a product of 3 to the 20th. So that's the best way to do 60. 61, when we had a number that was 1 more than that was divisible by 3, we did a bunch of 3s, and then we threw in a 4 at the end. So I think there we would have had 19 3s and 1 4. And 62. 62 is a number that is 2 more than a multiple of 3. So 62 is like 8 and like 11, where we put in as many 3s as we can. And then we throw in a 2 at the end. So that's 3 to the 20th, 23s there, and a bonus 2 at the end. And then by the time we get to 63, it's all 3s again, right? So we get 3 to the 21st. So that's the first part of the game, is trying to figure out what the pattern is. But now looking at this, and being a curious mathematician, as I hope many of you are, what question are you asking yourself? I know the question that I was asking myself when I first played this game is this question. Why 3? What on earth is so important about the number 3 that we should be trying to squeeze so many 3s into this? Just the other day, we heard that everybody's favorite number seemed to be 6. But we're not trying to squeeze a whole bunch of 6s into this. Our number system is base 10, but we're not trying to squeeze a whole bunch of 10s into this. Some people like to work in binary, but we're not trying to squeeze a whole bunch of 2s into this. We're trying to squeeze in a whole bunch of 3s, and then either a leftover 2 or 4. And so the question is, why 3? What is so special about the number 3 that it gives us the best way to win this game? So you should please try to think about that. By the end of the semester, or actually in 2 weeks from now, we'll have enough calculus to answer this question. This is actually a calculus question in disguise. But it can be answered. You can figure out why 3 by some experimentation without calculus. If you want to really prove why 3, then for that, we will need some calculus. So please enjoy this game at home. Please play it responsibly, and we'll see you back next week.